Hi friends, this is Mauli here and welcome you all for the 9th session of the ARM based development course. In this session we will be touching upon addressing modes, and once I say it is addressing mode means it is the data transfer instructions. Okay, so far in the instruction set we have seen data processing part of it. Now we will be talking about data transfer instructions. So you know that ARM is a RISC processor, and there are only two varieties of instructions which access the data. They are load and store. Okay, so but ARM supports lots of different addressing modes which you can use it with those data transfer instructions. So we will be covering the first three modes in this session. Addressing mode 1, we will only see the examples because I have already talked about this in detail. Then we will go into mode 2 and 3 with a little more details about what is happening inside the processor when these modes are activated by executing a specific instruction which belong to one of these modes. Now let us see first. There are basically 5 addressing modes supported by ARM. The first mode is associated with the shift operands which are meant for data processing instructions or maybe for any other load store instructions. So once I say shifter operands, that means it is the RM. Okay, there are two operands RN and RM. We talk about RM here, the second operand which goes to the shifter, barrel shifter in the instruction in the ARM processor, and then these two are specifically meant for load store. The first one is for the word and unsigned byte. Okay, I will explain you. And then this is about half word, that is word means 32 bits, half word is 16 bits, and loading of signed byte. Okay. Then multiple store is also another feature supported by ARM. We will be talking about this in the next session. And load and coprocessor instructions we are not going to be talking about. This instruction we are not going to be touching now. We will talk about this when we get to the coprocessor interface. Now addressing mode 1. Okay. In this there are basically 11 formats, different formats which we saw earlier. I will just, to refresh your memory, I will give you one example of each, and then we will go to the addressing mode 2. Now generic instruction format is opcode followed by the conditional code which decides whether this instruction has to be executed or not, and then yes, if you add append to the instruction, it means that whether this instruction can modify the CPSR of flags or not, and this is the destination register, and RN is one of the operands, and the RN, the second operand, goes through the barrel shifter, and we are going to talk about what all different ways we could modify the RM operand for the instruction. Okay. Let us see an example. A simple example is hash immediate. That means we can mention an immediate constant. If you recall how many bits are supported for an immediate constant, it is 12 bits. Okay, so I can maximum write starting from F 3 Fs. Okay, into 4 12 bits. So here this constant is coming along with the instruction, and then that gets moved into R0. If you recall, move instruction is a single operand instruction, so there is only one operand and then one RD. Okay, this operand has to happens to be RM, and another single operand instruction which is the another single operand instruction MVN. Okay, if you remember, we talked about that in the last class. Okay, now second format. As I mentioned, we are talking about what all we can do with the RM here, right? The second operand. Now add instruction has two operands. R0 is equal to R1 plus R2. So in this case, the second operand is a straightforward register. Okay. So is there any operation done by the barrel shifter here for this register? No. The value which comes from the register file goes to the shifter without any changes, because it enters the ALU without any modification, where you are not mentioned any shifting operations or rotating operation for this operand in this instruction. Okay, what is this EQ? You should be able to tell me, right, about this. EQ is a conditional code which corresponds to whether zero flag is set or not. If zero flag is set prior to the execution of this instruction, then this will be executed. Otherwise, this instruction will be skipped. Okay. Now, next example, we are having a register RM with a shift operator and an immediate constant. This is a logical shift left. I have given an example here, and this is a constant which is a 5-bit constant, if you remember. So a typical example could be this instruction. So I am giving different kinds of instruction for you to understand. When you see such instructions, you should be able to understand what is happening there, because I am introducing only the instruction which you are already aware. So before I explain this, please remember this instruction is about Boolean arithmetic or operation, and S is for saying that this instruction can affect the signal conditional flags in the processor, and R3, R2. So on R2, what are we trying to do here? We are trying to do a logical shift left by 4 bits, and then we are moving after the logical shift left of the value in R2. We are doing a Boolean arithmetic operation, that is R operation, Boolean R operation with the contents in R3, and then the result is written into R1. Now, when I say that this flag S is here, that means this instruction can modify the conditional flags after this instruction is executed. Now, what are the flags will be affected by this? In any logical operations, if you recall, except the sign flag, the zero flag and the carry flag, as well as the negative flags. Okay, overflow flag will not be affected, except that other 3 flags will be affected based on the result that is written into R1 here. So this is about logical operation with a shift operation. Okay, it could be any other different operations could be mentioned. Now another type. Now if you saw here, the shift operation was done based on the constant, the 5-bit constant which was given along with the instruction. Now there is a possibility, using this instruction we can always get the lower 8 bits of the register R5 as the how many bits that need to be performed. Okay, that operation logical shift left by how many bits, how many times, that is given by the lower byte of the register mentioned here, which is R5, happens to be R5. So whatever is the lower byte in R5, that many times this logical shift left will be done on the content of R4, and that value is Boolean and will be done with R3, and the result is written into R1. But there are some conditions here. This not equal to says that this instruction can be executed only when zero flag is cleared prior to this execution, and then S indicates that after this instruction, in case if this instruction is executed, if zero flag was cleared and this instruction is executed, then you will have the results of 3 flags, except the overflow flag. Other 3 flags will be affected by the value written into order. Okay, so I hope by now you should be clear about what is each instruction is doing. Now this is a other, you should be able to find out the differences between different formats. There are minor changes, but you should be able to identify them. So this two are LSL operations. Now you are seeing LSR, that means logical shift right. The same thing what I explained for this is true here. Only thing is, this many times the logical shift right is done. That means the bits are shifted to right, and then the MSB part will be filled with zeros because it is a logical shift. Now all this you understand. Now move, it is actually moving the value from R4 to R1 after performing this operation on the content of R4 into this. One more thing that you should remember, in all of these operations, whatever is the operands Rn or Rm, the values of those operands are not disturbed by any of them. Okay, only the RD, the destination registers, are modified, and you are free to use any combination, any kind of registers. In fact, you could use the same register in all the places too. Though some if you are using the R15, which happens to be a program counter, there are some restrictions. Other than that, you will be able to use all the registers. So if you recall the data part of the ARM, all the register contents are copied from the value. So the shifting operation or whatever happens is not happening on the register itself. The register values are copied and the barrel shifter is doing it. So please remember, none of these registers, operand registers, will get modified because of executing this instruction. Only the RD will be modified, provided these conditional codes are there. If it satisfies, this instruction is executed, then RD will be changed, and correspondingly based on whether you are doing an arithmetic operation or a logical operation, all the 4 flags will be affected if it is arithmetic operation, except for the overflow flag. Other 3 flags will be affected if you are doing a move or boolean logical operations. Okay, this will, I am summarizing this, so I won't be explaining this again. Okay, now let us go to the different mode, LSR, RS. So it's same as LSL, RS. Only thing is the shifting, the how much of amount of shift needs to be done is taken from the register. If you see here, the same register is used here, so no issues. What it will do, whatever is the value of R4, that many times the content of R4 is shifted to the right, logical shift is done to the right, and then that is moved into R1. But because it is NVN, it is the negation of this particular value is done. That means every bit is the inverse of that bits are done, and then the value is written into R1. Now what is this condition? MI is a condition code for minus. That means if the sign flag is set, that means the it's a negative result is there because of the previous operation somewhere, and then only this will be executed, and based on this movement, any flags will be affected based on what is written into R1. So if you see, you will see different instructions with different names here based on what EQ condition or any condition that you are choosing, and then whether you are using the S flag or not. So you will have lots of varieties of instructions here. Now what does it do here? It is similar to whatever LSL and LSR you saw. ASR is done, it is arithmetic shift right, that is bits are moved to the right, and if sign flag is set, it will be extending it. All ones will be coming in from the MSB side. Now this instruction is only thing I will explain you here. PL is a plus. That means if the the negative flag is not set, that means the previous result was a positive result, and this will be executed. So ASR with RS. Here you see I have chosen R1 for everything, so there is no issues. Okay, there are no issues in doing this. Only thing is you should be aware that after the previous value, whatever it was, then R1 is used by all this side of the instruction, and then it is overwritten by this. But based on the condition whether the carry flag is CS is carry flag is set, and then it will affect it will affect the flags, and then subtract operation will be done. That is, or whatever is the here, this operand minus this, whatever comes after this arithmetic shift. Okay. Now ROR, it is a rotate to the right. That means the LSB bit comes back to MSB, and RSB is what? Reverse subtract. That means instead of this operand minus this, you do whatever comes after this operation, that minus R2, and then write into R1, provided 0 flag is clear, and it will affect the all the flags, 4 flags, because RSB is a arithmetic operation. Now what is this? ROR with a RS. If the shift of how much of shift needs to be done, rotation needs to be done, is coming from another register, and here again I have used all R1. EOR is a XOR operation. So this operand and this operand XOR will be done, and the result is written into this, and provided carry flag is set. RRX is a rotate extended. That means carry flag comes into MSB and the 0 flag goes into carry flag, and compare instruction, if you recall, it does a comparison of these two values. In fact, effectively it will be subtracting it and then seeing whether all the flags will be set. Okay, all the flags will be affected based on the result of this, but none of these operands get impacted because of this subtraction, and it is done based on the condition here. So you can put any condition, but the S is not appearing here because it is default. This compare instruction always affects the flags. So even if you put yes or no, it doesn't matter. It will compare instruction will always be affecting the flags. So this summarizes the address mode 1. I intentionally took a little more time to explain you every instruction so that it summarizes whatever you have seen so far. So now you are ready to use any of this instruction in different combinations to achieve whatever you have in mind. So lots of things can be achieved because you have a whole lot of instructions at your disposal. Okay. Now after this session you will have much more to operate on. Okay. So let us now move over to addressing mode 2. Okay, what does it do? It supports, I told you that it is a data transfer instruction. That means what? This instruction helps us in moving some value between a processor and a memory. Okay, and what is it? This mode, what does it move? It moves a word, that means 32-bit word, 32-bit value, or an unsigned byte. So this is very important. Remember, I will explain with the example. It is an unsigned byte which is moved across. Now let us see what is the generic format of this instruction. LDR is a load register. This is store register. Load register means we are loading the register from the memory. Okay, so it is moving some data from memory to a register. Execute it based on this condition. And store means what? You are moving some register content into a memory location. Now B is optional because I told you that this instruction either moves a word. This addressing modes support either moving a word or a byte, that to unsigned byte. So if you mention a B along with the instruction, that means LDR B, if you say, that means you are interested in moving a byte. Okay, and then this part, please ignore it for a moment because this will be clear only when exceptions are handled. So during that time I will explain this. So for a moment you can ignore this. And then RD is a destination register. It could be the register which is getting the value from the memory, or this is the register from which the value is written into the memory. Now why are we calling this addressing mode? Because we are interested in knowing how can I generate the address, because when I say that it is something to do with the memory, then you should know which part of the memory this instruction is supposed to access, and where it is supposed to write a word or a byte, or where is it supposed to read a word or a byte. Now it has to be, this instruction should be given a proper address. Now there are different ways this address can be generated. Why they are supported, I will explain on the way. because it is to enable different kinds of support, data structure support for the compiler. This kind of different instructions are provided. So what are the different ways you can generate an address is what we are going to talk about in this session. Okay, so that's it about. Now this is, you don't have to memorize this. This is only I am giving you just to be aware how a particular instruction is coded, encoded in a 32-bit. Okay, please remember all ARM instructions are 32-bit byte. So any kind of instruction you see, they are all encoded into this particular 32-bit format. So based on the particular instruction type, the different kinds of flags or different kinds of bit positions are modified for the processors to understand that this is the kind of instruction coming from the memory. Okay. Now, if for the addressing mode 2, this value will be 0 1. If you remember, the data processing instruction had a 0 0 here. So processor will know, as soon as it sees this, it will know that okay, it's a addressing mode 2 instruction which is coming. So based on this value, it will decode the rest of the fields in the instruction. This already you are aware of it, whether what conditions on which it has to be executed. So this is you already aware. Now this bit also we have explained. If it is 0, how to interpret the immediate constant. If it is 1, how to interpret it. This also we addressed. So immediate offset means it's a 12-bit value which I told you, and earlier shift operation means a 5-bit value which can be here along with the RS value. Okay, that we have already talked about. Now these are the fields which are specific to the addressing mode. There are indexing bits, pre and post indexing bits, and whether the address is going up or down, or whether the offset is subtracted or added. Okay, that is implicit here. And whether we are transferring a word or a byte. I told you that this mode supports both a word transfer or an unsigned byte transfer. So that is interpreted by using this bit position values, either 0 or 1. And then this I will explain you. This is about whether the address has to be written into the base register or not, and whether you are doing a load operation or store operation is based on this. Okay, now I am mentioning a base register here. Okay, when I show a typical example, you will be very clear about it. Base register is the one of the 16 registers which are there in the processor. Whatever is the content of that is taken, and then an offset value which is given here is either added or subtracted, or it is rotated and then added, anything based on the type of the addressing mode. This offset is computed and added to the base register, which is mentioned by this value. It could be anything from R0 to R15, and then at that address, whatever is the content in the memory is either written into or read into this destination register. Okay, this is a simple explanation of this format. Okay, let us go forward. Now I am going to tell you how data path inside the ARM processor behaves. Okay, it is tied to the pipelining also. So please pay very close attention to this. If you understand this pretty well, then you will feel comfortable in understanding different instructions, and you will be able to understand why certain things are happening the way it is. Okay. Now I have given you a sequence of instructions here. What does it mean? By now you should be clear. Add, I am just explaining the first two instructions. Add means R1 plus R2, which is written into R0. Now this you are seeing for the first time. Okay. So for explaining the data path, I have to explain this ahead of the modes. So please I will explain you what does it do, so that you will be able to understand the data path. Now what is this str means? It's a store instruction. Okay. What is it doing? It is storing something into the memory. Where is it taking the value? It is taking from the destination. It is called RD, but actually it is not a destination here for a store, it is a source actually. So this R5, whatever is the content, will it write a word or a byte? there is no B here. Okay, I told you that if it is a B is written after str, that means it is a byte store, but it is a word store now. Okay, so the whole 32-bit value of R5 has to be written into some address. Now where is the address? What address? Processor doesn't know. So we are giving the instruction to that, saying that you take the value, the 32-bit value what is there in R2, okay, and then you subtract it by minus 804. Why 804? You can't give more than 3 hexadecimal value, that means 12 bits. Okay, that's the limit. If you give 1804, the assembler will give a book error. So when you put it into that square bracket, what does it mean? You compute this value, okay, take a value in R, whatever is stored in R2, and then subtract it from 804, and whatever the value you get, use that as a address. Send it to the memory, and then write this value into it. Okay, that is what is effectively we are informing the processor. Now, what is this exclamation mark? We are saying, okay, you are computing by doing this operation, but can I change this R2 after this? That is a optional one. If you mention exclamation mark, that means after this change, you can override the value in R2. Okay, you should. I hope you understand this. So if there is no exclamation mark, it will be the value from R2 is taken and then this is subtracted, and that in that address the R5 is stored, but it will not change the value of R2 after the execution of the instruction. Whereas if I put exclamation mark here, it will, after storing it, it will always change the value in R2. Okay, so that means you are advancing the value that R2 has by this much amount whenever this kind of instruction is executed. Now these 3 other instructions are given just to explain the pipeline. Okay, let us go into next stage now. Now see here, the first instruction is what you see here. It is fetched here. When this instruction moves into decode, the str is fetched, and when this str goes into decode stage, the another add, which is here, this instruction is fetched. Now during this time, the processor is trying to understand what is given here. Now it has to do so many things. It has to first of all do this arithmetic, generate the address, and then access the memory here to write the value in R5, and then only it can move into next instruction. So the execute stage of this instruction actually takes more than one cycle. Okay, execution is still not complete until this is done. So that is what I am trying to tell you, what exactly is happening during this time. So remember, the decode stage always is in the pipeline, right? So decode stage generates the signals meant for the next stage. So in this case, it is for the calculation of address, which is shown here. Okay, and then it has to, decode will be busy doing the control signal generation for transferring the data, which will be shown in the next, immediately after explaining this. So that is why this decode logic is not, if you see here, decode is not shown at this particular time. Okay, because this instruction's decode is delayed. That means the decode is busy with the previous instruction. Okay, in the pipeline. That is why you see a gap here. Okay, and then because of that, what happens? First calculation of address is done, and then the transfer happens. So remember, the str instruction takes 2 cycles first. Okay, to complete. Typical add instruction will be completed within 1 cycle, whereas this takes 2 cycles. Now let us try to see. I am showing you this diagram at this cycle. Okay, during the calculation of the address. Now what I mean by calculating the address, it is to compute this. So R2 has to be read. Which is R2 here? R2 is a base register, okay? Because offset is added always to a base register. We call it as a base register. So in this case, R2 is a base register. Where is it coming? This is coming from here, Rn. So R2, whatever is the content of R2 is given to the ALU. Why are we using ALU? Because you are doing a arithmetic here. Based on whether plus or minus is given, you will be either adding or subtracting this constant which has come along with the pipeline, okay, along with the instruction. This is coming along with the instruction. It is decoded into a 12-bit of value immediate constant which is coming along with the instruction. That is why there is a darkened path here. What does it mean? From the decode stage, this constant 12-bit constant is coming to this pipeline register into the barrel shifter. Now you may wonder why is this LSL 0 here? Because you are not mentioned any shift operation here. You don't see any ROR or LSL or LSR, ASR, nothing is there. So, but the data has to go through the barrel shifter because it is the particular this data part is designed this way. So any data coming in either through a register or through a pipeline, that immediate constant, it needs to pass through the barrel shifter. So when there is no shift operation mentioned in the instruction, the processor assumes it is a LSL 0. That is left shift logical shift left by 0 position. What does it mean? You are not modifying the value. Okay, if you recall, only LSL supports this #0. Other operations like shift logical right or arithmetic right or rotate right, if you put 0, it means something different. So that is why the logical left is encoded in the instruction as 00, and it is assumed here that it will be default set to 0 whenever it sees that there are no shift operation or rotate operation given along with the instruction. So for this particular calculation there is no shift operation. So now why is this coming through this? I told you that this is the immediate constant which is coming along with the instruction. When I say along with the instruction, it is decoded, it is part of the instruction, it is encoded into that. So it has been decoded by the decode stage and then it is passed on to the pipeline register and coming here. You see here 12 bits are there, 0 to 11, 12 bits are shown here, so that they come into this. Now this ALU has an option whether to perform A, just take this value, or do a plus B or A minus B. Now how will this ALU will be driven? Based on whether you have put a negative value or not, this will do the job. So now what happens in the address calculation, R2 is taken, 804 comes through this without any shift, and then it gets R2 minus 804 is done by the ALU, and then the computed value is going into the address register. Because you have written this whole thing into the square bracket, that means you are interested in accessing the address generated by this operation. So that needs to go to address register. Now you remember, address register is common for both data access and instruction access, because this supports a single unified data and instruction memory, the ARM7 what we are talking about. So because of this, when any memory access is done, this address register and the address bus, this is tied to a address bus, 32-bit address bus, is used by the data access. That means what? It cannot perform a prefetch during this time. That is why you see that during the calculation fetch is happening, okay, but not during the access. So what I mean by that is the address is a new calculator, that means that during that time this address register is already holding a PC instruction address referring to this this instruction number 4. So it is accessing that instruction now, and then once address calculation is done and it is overwritten into this address register, then the next cycle it will not be doing a fetch. That is why you see that there is no fetch here, there is a gap. please remember, always in this particular data path, data path, the address register holds the address for the next cycle what it is supposed to access. So that's why during the calculation already this access is happening, and this calculation is happening for computing the date address meant for the next cycle, which is a data transfer, because you are supposed to write some value into this address. So it is calculated here, and then actual accessing of memory is done in the next cycle. Now there is something happening here. What is it happening? You should be able to find out. Explain this yourself, because I told you that address register was fetching a previous instruction prior to this. Now next cycle is going to be taken over by the data access. That means the address, next address, instruction address, what needs to be fetched has to be saved back in the R15. Okay, and it should be saved by incrementing it by 4 and then writing into PC. Okay, so the previous this address is incremented and kept in the PC so that next time it can be used for accessing this instruction down the pipeline. Okay, so that address is incremented, and increment means it is incremented by 4, remember, and that gets written into PC. Okay, now this address register, where all is it taking inputs from? It is taking either from the increment, or it is taking from the register file, or it could come from the ALU. At one time only one of these input lines will be activated so that they drive the address into the register. Okay, not these two, or any two cannot be there, right? Only one can be driving a particular value into the address register for the next access memory cycle. Similarly, during that time, whatever is the previous content is taken and incremented and written into PC. Okay, I hope this whole thing is clear to you now. Okay, if you don't understand, please listen to this explanation again, or look at the diagram, and this you will be able to make out what is happening. Okay, shall we go to the next explanation, next cycle, what happens? So please remember, in this instruction there is a exclamation mark. So we are supposed to write whatever the value you are accessing, the offset you have added with the R2, you are supposed to write into R2. Now you may, if suppose you are very critically evaluating this particular diagram, trying to understand this, you would have noticed that this is not enabled. That means the offset after computing the new address, it is not returning to the R2 immediately. It is done anyway. This execute cycle is with the same instruction. Okay, it can be done in the next cycle, but why is it delayed? I will give a slight explanation now, but it will be clear when I talk about the data abort. See, the processor is generating the address with the hope that the memory will provide the data or will allow the writing of the data into the memory. So if suppose if the writing into the memory doesn't happen and data abort, then memory will give a data abort signal back to the processor saying that, hey, this address is not valid, you have to take some corrective action before executing this instruction. So an abort signal will come. If suppose assume, because the instruction says I need to modify the value of R2, okay, after this offset is computed, offset is added with the base register, if it has written into the R2, the old value of R2 is now overwritten. Okay, now suppose data abort happens, now processor has to restart this instruction after the corrective action is taken. I will explain you what is the corrective action later, but somehow assume the processor can start the same str instruction again when it encounters the data bus. In that case, what will happen? The R2 would have been already updated. Then you won't be doing what you wanted to do, right? The processor won't be doing what you intended to do. That is why until the memory cycle is completed, this register is not modified. Though it says, hey, I want to overwrite the value, it waits for the memory cycle to do complete and the data to come from the memory, or allowing the data to be written into the memory without any issue. Then in the next cycle, once the transfer is done successfully, then you can easily update the value. Now it is not that easy. The processor architecture should support it, because ALU should hold the value what it is computed now, so that it can be used for writing into the register in the next cycle. So I am just telling you why this is not grayed out. So it directly writes into this, but it doesn't write into the register file. Okay, I hope this is very clear to you. Now let us move on to next cycle. I have taken only this instruction which is of interest to us. Okay, now pipeline is explained, understood. Now if you remember, in this cycle what happens? The data transfer happens. What is this instruction? It is supposed to be doing the store. That means this R5 has to be written into the memory. Then this R5 has to go out to the data bus. How does it go? R5 is taken from this. This path is taken. So the decode logic is doing all the controls so that this path is activated. Now the whole word goes out. Okay. At this moment, I will explain you this also. If there was a str byte, it is supposed to only take the byte value, okay, based on which byte you want to write. So it is always, when you say byte from the register, it will always take the lower byte of the register, but based on the address generated, it may have to be written into one of the 4 locations. Okay, so I will explain you what I mean by one of the 4 locations. Suppose this is the this is 1000. I always take 1000 because it is easy to understand. So this is the lower byte 0, 1001, 1002, 1003. Now suppose the address what you have generated has resulted in one of the values. Okay, it could be 1001 or 2 or 3, and you have written a B here. Then what happens? That particular LS byte from R5, okay, has to be written into a particular byte of in the memory. So the memory could be because if you remember, this ARM processor is can be integrated with any memory, right? So what is done by this unit is, it will replicate the value in all of them, all the bytes, and then write into generates that value into the database. Suppose you are writing 5, that 5 is written into each of the bytes. Okay, now you may wonder, why is it? You want it right? No, all 5 5s into the values. No, the memory is supposed to only write 1 byte based on the address what is generated in that location only, but it is given a flexibility that if it wants, it can pick the byte from directly from this byte or this or this or anything. Okay, it depends on the way memory is interfaced. That is the job done by this byte. So this question mark is given, provided if it is a byte access, this will get activated, and then the LS byte will be taken and then replicated in all the data buses. Data buses from D0 to D31, right? So it will write the same byte value into all these positions and give it to the memory. The memory can decide to do based on the address which is coming out here. So the address whatever 1001 or 2 will come out through this, and data will go out through this. So these are the data bus and address bus. Okay, I hope this is clear to you. Now let us see what happens. I will explain some more things. I have explained this part of it. R5 goes out and into the data bus, and I told you that ALU is holding the previous computed value in its internal register and then writing into the, where is it writing? It is writing into R2. Now R2 is modified because there is a exclamation mark. So that address is written into, and the value is also the byte value or a word value is written to the memory also. Okay, it is completed now. The data transfer has been done now. So it is free to modify the register here. Now what is happening here? I told you when this data transfer is happening, it has to generate an address for the next cycle because it has to do a prefetch. It has earlier saved that value into the PC. Now it goes out here into the address register so that now it can access the program, the next value, because next cycle this anyway this instruction is coming out of the execute state. So the next instruction will come into the execute state and address access will happen now. Okay. So the instruction, the next instruction address is going out from the PC. That is why it was saved earlier and then now taken out from this. Please remember, this value whatever is there in the address register is overwritten by the address calculated by this. The previous PC value would have been gone. So that has to be kept there in the PC. That is why it is done this way. Okay. I hope this is very clear to you. Now let us see. I explained the whole thing with a load. Now what? Store. Now what happens with the load? With the explanation so far, you should be able to deduce what happens in the load. What will happen? Let us see. Suppose it was a load. This will be same because computing the address is same. Okay. Now you can instead of saying store, you are saying that you compute the value address and then give me the word in that address and copy it into R5. Okay. For a moment assume that it is an LDR. Now this has to, something has to be different here. This will be same but something has to be here different. What it needs to be? This will be same. Okay, the writing the new value into the register will happen anyway, but instead of now driving the data bus with the value in R5, you are going to take the data in because you are loading from memory to a register. So this will be opened up. So the data which comes in from the memory will come through this, and now you see there is no way it can get into the register now, right? It cannot go in any other path. So it has to come to the shifter and then return into this value. Okay. So that's the way a data in happens for load. Now you have a problem now. I told you this particular path is used for writing the address, correct? Now I am saying that data also has to go through this. It cannot happen together. Now is the catch. Understand this. When a particular value is loaded from memory, in that cycle the value comes and sits in data in. It is not taken inside because there is, first of all, there will be a delay of introducing so much. Okay, if it has to be done in a clock. Another reason being, this path is already used for writing back in case if there was a write back instruction. So storing happens in the another cycle. So compared to store, the LDR takes one more cycle to complete. Again, let me explain again if you are not followed. I am telling that instead of STR, LDR is there. What does it mean? You compute the offset and then access the memory in that address and store that value into R5. Now the computing the address is done by this cycle, and in the data transfer cycle that address is put already, the data has come in. So the data is from memory, it has come into this register and it stays there. During that time this value has to be written back, that happens without any disturbance, and then one more cycle is taken. That time this data will come through this and there won't be any shift here and it will not take any input. The ALU also will pass this value out and now it will be written into R5. So the memory content coming from memory lands here and then goes through this and finally lands into R5. Till then this execution is not complete, this instruction is not done until the value from memory goes into R5. So that is done. So this actually completes the transfer. Okay. Now that is why I have put some note here. It will take one more cycle. You can read through. LDR instructions follow a similar pattern except that the data from memory only gets as far as in data in register on the second cycle, and the third cycle is needed to transfer the data from there to destination register. So from here to destination register will be one more cycle if it was a LDR. Okay, I think once you understand this, the rest of the part of the presentation will be different ways of using the instruction. Okay. Now let us see one by one. I told you LDR or LDRB or STR or STRB based on byte. Now there is a first mode which is called LDR STR conditional flag B and expression. What does it mean? I will give an example. See, here you have to pay a little attention. The dot data, okay. This dot data is a assembler syntax to say that it is a data segment. It means you are declaring a data. Now num1 is some variable I have given. I have declared it as a word and then writing it 1 2 3 4, initializing it. That means before the program is loaded, the assembler and the linker loader takes care of particular location it allocates for num1 variable and then loads this value 1 2 3 4 in it. Assume it happens to be a 1018. This is the address, okay, allocated to that. So it is there. Prior to that condition, there is also I am making sure that an ABCD is stored in the memory. So this I am showing a memory contents of 32-bit wide. So 1 2 3 4 is only occupies 16-bit. That's why you see that there are zeros here. I think this will be very clear to you. Now I am having an instruction called LDR, same load, R3 equal to num1. If I give this particular instruction, what am I trying to do here? I am trying to see when I am declaring a variable of num1. If I want to use that in my register inside my program, I will not be able to use it until I know the address where it is stored. Okay. So it has to be loaded. The address at which the num1 is declared. Assembler, linker, or loader has done the job, but now I want to get the address. This is the instruction used. Now how is it done? When I say this, the address of num1 is written moved into R3. How is it computed? It is internally done by this instruction is changed in such a way that a PC value, whatever is the current PC value, PC is what? The R15 is modified. It is taken. PC is not modified, but only the PC value is taken, and then some offset is added to that. It's a PC relative addressing. What I mean by that? When this num1 is there in the program, it should be within the range of plus or minus 32 megabytes. Okay, because 12-bit offset, and there is a detailed explanation that for that. But for now, you remember that, you understand that this particular variable will be in some range, within the range of some existing PC value. So what is the difference between that? The assembler can deduce it based on the current PC value, because it knows where it is placing this program into the memory, and it knows that where the data is placed, so it will accordingly place it in such a way that it can be accessed with respect to the PC. So this instruction will inform the processor. You take the PC value now, add some offset which is given by this instruction, and then you will get the address of num1 here. Okay, so that is what is done by this loader LDR instruction. Now what does this do? You can do the same thing for not only for getting the address of any data variable in your program, you can also get a address of a label. See, now in a typical assembly program, you can always write some label, alphanumeric value followed by a colon. That means this is the instruction and this is the label for that instruction. Now where is this particular instruction stored? It is stored from the current PC of this instruction plus 4. So it is very easy for this instruction to inform, okay, to compute the value of label, and then right now it is moved into PC itself. That means what happens? Whatever is address here is moved into PC. So effectively now PC will be moved to this register, to this particular instruction. You may wonder that okay, anyway it may fall through also, it will come here, but there is a minute difference between these two. When I move a new PC value, the pipeline is flushed and then again started accessing from this instruction. So there will be a minor performance change, but I am just explaining this for you to realize that how a label also can be given as another parameter to the LDR instruction, which is this type of instruction, and then you can get the value. Also you can write into any register or you can write into PC itself. That means it will move to that particular value. Please remember, you can write into PC only the program address, because here label actually points to a program address. You can't put PC comma equal to num1. It is a data, some data you have stored, not a actual. This is not holding any program. So if you do that, you will have a problem, and sometimes assembler also is intelligent enough to give an error. Okay, but be careful when you are modifying these values. But you should try this out in your simulator and understand what is happening. Okay, so these are the values of new R3, because num1 is stored here, so R3 will be having this value, and R15 will be address of move instruction. Okay, now tell me what is happening here. When I say this anyway num1, whatever the value is 18, it plus 4 is done, and that is moved into R3. That's why R3 will be with 1C, and R15 I have just intentionally changed. Instead of PC I am making it R15 just to make it clear to you that it could be anything. You can mention it as PC or R15. And when I say label -4, label is the next instruction, -4 is this instruction itself. So when you execute this instruction, PC will keep loaded with the same instruction. So you will see that in the simulator it will keep executing this instruction. It won't move forward, it won't go anywhere, it will be here. Okay. So address of this instruction -4. This one. So load the same instruction. So this is the first expression. Let us go to next one. Then this is the load part. Go to so okay. Is going to now